On September 1st, 1859, British astronomer Richard Carrington was sketching a group of sunspots when two brilliant patches of light suddenly appeared across the sun. Within hours, telegraph systems across Europe and North America began behaving strangely. Operators received electrical shocks, equipment sparked, and some stations discovered they could transmit messages even after disconnecting their batteries. The sun had reached across 93 million miles of space and interfered directly with human technology. But that was 1859. Today, satellites, GPS, aviation, communications, navigation, and electrical grids all operate beneath the same star. A comparable event would encounter a civilization far more vulnerable to what the sun can send toward us, and scientists are still discovering that some of their assumptions about solar activity were incomplete. In 2025, researchers reported evidence that particles inside solar flares could reach temperatures dramatically higher than traditional models assumed, potentially changing how scientists understand the physics inside these enormous releases of energy. Ancient tree rings preserve another warning. Earth has experienced solar particle events even more extreme than anything directly measured during the technological age. The sun appears remarkably stable. Most of the time it is. But hidden inside its magnetic activity are events powerful enough to reach Earth and expose weaknesses in systems we now depend on every day. We make these long form space documentaries because we love this stuff, and so do you. If you want to keep exploring with us, subscribe, and we'll be here whenever you need a quiet journey through the cosmos. To understand where that danger comes from, we first need to understand what the sun actually is. It starts with the forces moving beneath the surface of the sun. Before we can understand what the sun is capable of, we need to see it for what it actually is. The bright disk above us invites familiar comparisons, yet almost every instinct we carry from life on Earth fails inside a star. The sun is not burning. Fire depends on oxygen feeding a chemical reaction. The sun operates through nuclear fusion, a process in which hydrogen nuclei are squeezed together by overwhelming heat and pressure until they become helium. A small portion of their mass is transformed into energy, and that energy has sustained our solar system for billions of years. Deep within the core, temperatures climb to roughly 27 million degrees Fahrenheit. The pressure there reaches about 250 billion times the atmospheric pressure at Earth's surface. Matter behaves in ways impossible to recreate for more than brief moments inside laboratories. At those extremes, ordinary gas becomes plasma, an electrically charged state in which atomic particles move freely and respond to magnetic forces as readily as gravity. You might expect that energy to race outward immediately. It does not. A single packet of light can spend anywhere from 10,000 to 170,000 years scattering through the sun's crowded interior before finally escaping the surface. Once free, the journey changes completely. The same light crosses the 93 million miles between the sun and Earth in only 8 minutes and 20 seconds. The visible surface, called the photosphere, glows at nearly 10,000 degrees Fahrenheit. Above it lies the chromosphere, then the corona, the sun's vast outer atmosphere. Strangely, the corona reaches well beyond 1,800,000 degrees Fahrenheit, making it dramatically hotter than the surface beneath it. Moving away from a heat source should produce cooler temperatures, yet the sun refuses to follow that expectation. Even after decades of study, this remains one of solar physics' most enduring puzzles. Its structure is straightforward enough for us to keep in mind. At the center rests the core, surrounded by the radiative zone, where energy slowly works outward through countless interactions. Beyond that lies the convective zone, where enormous currents of plasma rise and sink. Then come the photosphere, the chromosphere, and finally the corona, extending far into surrounding space. Nothing inside this star remains fixed. Plasma is constantly flowing, twisting, and circulating beneath the surface. That motion generates an immense magnetic field, wrapping around the sun like an invisible framework. We cannot watch those magnetic lines directly, yet they shape nearly every dramatic event the sun produces. What appears steady from 93 million miles away is in reality a restless engine storing tension over time. Magnetic forces stretch, fold, and gather energy without announcing when they will finally release it. That hidden process, unfolding beneath the familiar sunlight reaching your face each day, defines the true rhythm of our nearest star. Imagine tracing a single invisible thread across the sun, then returning a month later to find it stretched, twisted, and pulled into an entirely different shape. That unseen transformation drives nearly every dangerous event our star can produce, even though the process unfolds beyond ordinary sight. Unlike Earth, the Sun does not spin as one rigid body. Its equator completes a rotation in about 25 days, while regions closer to the poles can take nearly 35 days. Plasma, an electrically charged fluid rather than solid rock, allows different parts of the sun to move at different speeds. Over time, those uneven motions reshape the magnetic field again and again. We can picture the field as countless invisible lines extending from one magnetic region to another. As the faster equatorial regions gradually pull ahead of the slower polar latitudes, those lines become stretched and wound tighter with every rotation. The effect resembles a rubber band twisted repeatedly from one end. Each turn stores more tension inside the magnetic structure itself. Eventually, that strain becomes too great to remain hidden beneath the surface. Sections of the magnetic field force their way upward through the photosphere, interrupting the normal rise of hot plasma from below. Those disruptions create sunspots, regions that appear dark only because they are cooler than their surroundings. Their temperatures remain close to 6,300 degrees Fahrenheit, while the surrounding surface approaches almost 10,000 degrees Fahrenheit. Even so, a single sunspot isolated against the night sky would shine more brightly than the full moon. Centuries ago, the Italian astronomer Galileo Galilei carefully watched those spots drift across the sun. Their movement revealed that the sun rotates, overturning the belief that the heavens were perfectly unchanging. Continued observation eventually uncovered something even more remarkable. Different latitudes rotated at different speeds, exposing the hidden engine that keeps winding the sun's magnetic field. The process never truly stops. Across an average 11-year solar cycle, magnetic tension continues accumulating until activity reaches its peak. Around that maximum, the entire magnetic field reorganizes. The north and south magnetic poles exchange places, completing one of the most extraordinary cycles in our solar system before beginning again. As opposing magnetic regions are pushed together, the field can no longer maintain its strained arrangement. A process called magnetic reconnection takes over. In plain terms, imagine forcing two opposing magnets into positions where their invisible fields suddenly rearrange. Stored energy is released in an instant, producing an enormous burst far beyond anything created by ordinary combustion or mechanical force. That sudden release is a solar flare. Its strength depends on how much magnetic tension accumulated beforehand, making every flare the final expression of energy stored over weeks, months, and even years. During September of 2025, New research revealed that this stored energy reaches levels far beyond what decades of established models had estimated, changing how we measure the sun's magnetic power without altering the ancient process that has governed it all along. Energy stored for months can disappear in an instant. When magnetic tension finally gives way, the sun does not produce an ordinary explosion. Instead, it converts magnetic energy directly into electromagnetic radiation, releasing an immense flash across the entire spectrum at once. X rays, ultraviolet light, gamma rays, visible light, and radio waves surge outward together, racing into space at the speed of light. The largest solar flares unleash an amount of energy comparable to billions of nuclear weapons detonating within only a few minutes. We classify these events using a scale developed by the National Oceanic and Atmospheric Administration. Categories begin with the faintest flares and increase by factors of 10 until reaching the highest letter, known as the X class. The scale has no upper boundary. An event rated 10 times higher carries 10 times more energy, and the numbering continues as long as nature demands. For Earth, speed changes everything. Once a flare erupts, there is effectively no opportunity to stop its radiation from arriving. The light itself crosses the 93 million miles between the Sun and our planet in 8 minutes and 20 seconds. By the time observatories detect the event, analyze it, and distribute alerts, the first wave has already reached us. You experience the first effects far above the clouds. The radiation strikes the ionosphere, the electrically charged layer of Earth's upper atmosphere where many radio signals travel before returning to the ground. Extra energy rapidly alters that region, increasing ionization, meaning atoms lose electrons and become more strongly charged. Radio waves passing through this disturbed layer can weaken, bend unexpectedly, or disappear altogether. The consequences spread quickly through familiar systems. Global positioning system signals lose accuracy. Aircraft communicating across oceans encounter degraded high-frequency radio links. Ships navigating distant waters experience interruptions. Emergency service communications can become unreliable across the daylight side of Earth, all within minutes of the flare's release. One event demonstrated how difficult these eruptions are even to measure. On the 4th of November, 2003, during the period known as the Halloween storms, instruments aboard the geostationary operational environmental satellite recorded a flare reaching class 28 before their sensors became saturated. Later analysis suggested the true intensity may have fallen somewhere between class 34 and class 45. The detectors had simply reached the limits of their design. The effects are not confined to observatories. During the severe geomagnetic storm of May 2024, precision farming equipment across parts of the American Midwest lost dependable positioning during an important planting season. That disruption drew far less attention than the colorful auroras seen across unusual latitudes, yet it revealed how deeply modern infrastructure depends upon uninterrupted space weather conditions. Still, the flare itself is only the opening act. Its brilliant flash announces that magnetic energy has been released, yet the greatest danger often follows later. A slower, heavier wave begins expanding outward from the sun, carrying something far more substantial than light alone. It is called a coronal mass ejection, and it belongs to an entirely different class of solar event. Light reaches us first, then the sun sends something far heavier. A coronal mass ejection is an immense bubble of magnetized plasma, meaning electrically charged gas bound together by its own magnetic field, hurled outward from the corona into the solar system. Each eruption carries billions of tons of solar material, expanding across space at speeds ranging from roughly 560 miles per second to nearly 1,900 miles per second. Unlike the radiation from a flare, this expanding cloud does not arrive almost immediately. Its journey usually lasts between 1 and 3 days. That delay creates the only practical warning window available during major space weather events, giving scientists time to estimate its path, while operators prepare satellites, electrical grids, and communications systems for what may follow. The greatest danger does not come from the plasma itself. Instead, it comes from the invisible, magnetic field traveling inside the eruption. As the cloud reaches Earth, that magnetic field encounters our planet's magnetosphere, the magnetic shield surrounding Earth. When the two magnetic systems connect efficiently, enormous electric currents begin flowing through the upper atmosphere and even into the ground beneath our feet. Everything depends upon orientation. If the incoming magnetic field points southward, opposite Earth's northward field, the two systems lock together far more effectively and transfer tremendous amounts of energy. When the incoming field points northward, much of that energy is deflected instead. Scientists cannot determine this crucial alignment until the coronal mass ejection reaches a monitoring spacecraft stationed about 930,000 miles from Earth. By then, only about 30 to 60 minutes of final warning remain. Those electrical currents spread through anything capable of conducting electricity. Long transmission lines become especially vulnerable, allowing geomagnetically induced currents, meaning electricity generated by changing magnetic fields rather than power plants, to flow into massive transformers that were never designed to handle them. History has already demonstrated the consequences. On the 13th of March, 1989, a coronal mass ejection struck Earth and collapsed the Hydro-Quebec electrical grid in only 92 seconds. Approximately 6 million people lost power for 9 hours, while transformers as far away as New Jersey suffered damage from the same storm. That event followed a powerful Class 15 solar flare. The Carrington Event of 1859 was almost certainly larger still, and its associated coronal mass ejection crossed the distance to Earth in only 17 hours and 36 minutes, among the fastest transit times ever reconstructed. Modern risk assessments, prepared by Lloyd's of London, estimate that a comparable storm today could leave between 20 million and 40 million Americans without electricity for 1 to 2 years. The greatest obstacle would not be repairing wires. It would be replacing enormous custom-built transformers requiring years to manufacture. Perhaps the most sobering detail arrived much later. During July of 2012, the Sun launched another coronal mass ejection comparable to the Carrington Event. Earth escaped for one reason alone. Our planet occupied a different part of its orbit, missing the eruption by only 9 days. There are moments when history changes without anyone noticing. No cities fall, no broadcasts announce disaster. Life continues exactly as before, while millions remain unaware that the outcome depended entirely upon where Earth happened to be in its orbit around the Sunday. On the 23rd of July, 2012, one of the most powerful coronal mass ejections ever recorded erupted from the Sunday. Instead of racing toward Earth, it crossed a different part of the solar system. Waiting there was the Solar Terrestrial Relations Observatory Ahead spacecraft, built by the National Aeronautics and Space Administration to study the Sun from another vantage point. The spacecraft passed directly through the eruption and survived, returning an extraordinary record of the event. The cloud moved at roughly 1,000 550 miles per second, placing it among the fastest coronal mass ejections ever measured. For comparison, the eruption responsible for the Hydro-Quebec blackout in 1989 traveled at only about 620 miles per second. Speed alone does not determine danger, yet faster clouds compress space ahead of them more efficiently and deliver their magnetic energy with far greater force. The measurements revealed something even more concerning. Embedded within the plasma was an unusually powerful magnetic field, oriented southward, precisely the alignment that couples most effectively with Earth's magnetosphere. It represented the configuration space weather scientists hope never to see approaching our planet. Physicist Daniel Baker of the University of Colorado led much of the subsequent analysis. Speaking in 2014, he concluded that if Earth had occupied the path of that eruption, it would likely have produced the most powerful geomagnetic storm in recorded history. He described the resulting consequences as catastrophic and long-lasting, reflecting the vulnerability of modern electrical and technological infrastructure rather than any change in the sun itself. Despite those conclusions, the event passed with remarkably little public attention. Most people living today have never heard about the eruption that narrowly missed our planet. It remained largely within scientific literature and professional discussions, even though it demonstrated that an event comparable to the Carrington storm belongs to the present as much as the past. The Solar Terrestrial Relations Observatory Ahead spacecraft endured the impact because it had been engineered specifically to operate within the harsh environment surrounding the Sunday. Its instruments continued transmitting detailed observations, allowing researchers to reconstruct the eruption with an accuracy impossible during earlier centuries. Those measurements transformed a fortunate escape into one of the most valuable space weather records ever collected. The near miss also changed scientific priorities. It reinforced the need to understand how frequently the sun produces eruptions of this scale and encouraged greater investment in forecasting hazardous space weather. That perspective became even more important after the discoveries announced during September of 2025, when evidence suggested the sun stores more magnetic energy than established models had predicted. Together, those findings point toward the same conclusion. Our nearest star remains fully capable of producing extraordinary events within the modern age, and the longest record of those events is preserved far beyond observatories, inside the oldest natural archives on Earth. Long before telescopes tracked the sun day after day, Earth had already begun keeping its own record. It did not write in ink or stone. Instead, each passing year left a chemical signature inside growing forests and accumulating ice, preserving a history that would remain unread for centuries. Every year, a tree adds another growth ring beneath its bark. During that season, it also absorbs radioactive carbon-14 from the atmosphere while converting sunlight into food through photosynthesis, the process plants use to transform light, water, and carbon dioxide into stored energy. Most of the time, those yearly traces change only gradually. Occasionally, one ring stands apart from every other. Radioactive carbon-14 forms high above Earth when energetic particles strike nitrogen atoms in the upper atmosphere. A stronger shower of particles creates more radioactive carbon-14, which is then carried through the atmosphere before becoming part of living trees across the world. Each annual ring locks that chemical fingerprint into place, preserving a remarkably precise calendar extending thousands of years into the past. In 2012, physicist Fusa Miyake examined ancient Japanese cedar trees and identified an astonishing signal. Rings dating to either 774 or 775 contained a sudden surge of radioactive carbon 14, unlike anything expected from ordinary solar activity. Estimates suggest the particle output responsible may have reached roughly twice that associated with the Carrington event. One remarkable tree might have reflected only a local phenomenon. Researchers therefore searched much farther. Matching chemical spikes appeared in tree rings from Russia, Germany, New Zealand, the United States, and Siberia. Every location recorded the same unusual increase during the same year. Whatever happened had affected the entire planet almost simultaneously. Another substantial increase emerged in rings dating to 993 or 994. Although smaller than the earlier event, it still exceeded estimates for the Carrington event by a considerable margin. The pattern suggested these extraordinary outbursts were not isolated curiosities. Evidence soon arrived from an entirely different archive. Ice cores extracted from Greenland and Antarctica contain annual layers formed as snow, gradually compressed into ice. Within those layers, nitrate chemistry preserved the signatures of unusually intense particle bombardment during the same periods identified in the trees. Independent records, separated by continents and formed through different natural processes, pointed toward the same moments in history. Scientists eventually extended the search even deeper into the past. Additional evidence indicates possible extreme solar events around 660 years before the Common Era, 5,480 years before the Common Era, and 7,176 years before the Common Era. Together, these discoveries stretch the record of intense solar activity across roughly 9,000 years. The event discovered by Fusa Miyake is now known as the Miyake Event. No historical account describes widespread technological disruption because none existed to observe. Its only enduring witnesses were trees adding wood beneath their bark and snow settling across distant ice sheets. Researchers continue debating the exact mechanism, though the leading explanation remains an exceptionally powerful solar energetic particle event, possibly accompanied by an enormous solar flare and coronal mass ejection. Most striking of all, these ancient records suggest our brief century and a half of direct solar observation may represent only a small chapter within a far longer and more turbulent history. Scientific understanding sometimes advances through a new discovery. At other times, it changes because a deeply trusted assumption finally gives way. For decades, one such assumption rested beneath nearly every calculation describing the hottest moments inside a solar flare, rarely questioned because it appeared to fit everything researchers could measure. Inside solar plasma exist two principal kinds of charged particles. Electrons carry negative electric charge and possess very little mass. Ions, the positively charged atomic nuclei left after electrons are removed, are vastly heavier. Both move through the magnetic environment together, exchanging energy through countless interactions. For more than half a century, solar physicists assumed those interactions forced electrons and ions toward the same temperature during a flare. The reasoning seemed sound. If energy passed rapidly between both particle populations, then measuring one would reveal the other. Electron temperatures could be estimated using spectroscopic observations, where light is separated into its component colors to reveal the physical conditions inside the emitting plasma. Directly measuring ion temperatures proved much more difficult, so the electron measurements became the accepted stand-in. That assumption spread everywhere. It appeared in textbooks, guided the interpretation of spacecraft observations, shaped forecasting systems, and became part of the mathematical foundations used by organizations such as the National Oceanic and Atmospheric Administration and the European Space Agency when studying hazardous solar activity. Then, during September of 2025, physicist Alexander Russell and colleagues at the University of St. Andrews published a new mathematical analysis in the Astrophysical Journal Letters. Their work focused on magnetic reconnection, the rearrangement of magnetic field lines that releases enormous amounts of energy during solar flares. Instead of distributing that energy equally, their calculations showed that the process favors ions far more strongly than electrons. The consequences were remarkable. According to the new model, ion temperatures inside solar flares can reach approximately 108 million degrees Fahrenheit. Earlier models generally placed the upper range between about 18 million and 72 million degrees Fahrenheit. The hottest particles inside a flare were therefore far more energetic than researchers had believed for decades. If those calculations continue to withstand scrutiny, they imply that solar flares contain substantially more stored energy than existing operational models have accounted for. That conclusion reaches well beyond academic theory because every prediction of flare behavior ultimately depends upon understanding how much energy the sun can release. Other experts immediately recognize the importance of the result. Physicist James Drake of the University of Maryland, who was not involved in the research, told National Public Radio that solar physicists had been missing something big. Alexander Russell himself described the calculated temperature as a crazy number, adding that even his own team found the result difficult to believe when it first emerged. The earlier models were never careless. Scientists relied upon the best observations available, using the easier measurement as a practical substitute for one that remained extraordinarily difficult to obtain. What changed was not their dedication, but the realization that the substitute had quietly concealed a fundamental difference for 50 years. That revised understanding now reaches into every model used to assess risks for satellites, electrical grids, and astronauts traveling beyond Earth's protective magnetic shield. Every forecast begins with a number. Behind each alert issued to governments, satellite operators, airlines, and power companies lies a chain of measurements translated into mathematical predictions. When those measurements change, the forecast changes with them, even if the sky above Earth appears exactly the same. The recent discovery does far more than adjust a technical detail inside solar physics. It changes the estimated energy budget of the most powerful solar flares, meaning the total amount of energy available to drive hazardous space weather. If the hottest ions inside a flare carry substantially more energy than previously believed, then decades of forecasting have started from a lower baseline than nature actually provides. Space weather prediction follows principles much like forecasting hurricanes or winter storms. Scientists gather observations, compare them with physical models, and estimate how severe an event may become. Those predictions determine practical decisions. Satellite operators place spacecraft into protective safe modes. Airlines redirect certain flights. Electrical grid managers prepare equipment and adjust operating conditions before disturbances arrive. Every one of those decisions depends upon models calibrated with flare energy estimates that are now being reconsidered. Updating those models is neither simple nor immediate, because every change must be tested against years of observations before becoming part of operational forecasting. Consider the satellites surrounding Earth. By the year 2025, roughly 9,000 active spacecraft orbited our planet. They support navigation, communications, weather forecasting, scientific research, financial transaction timing, and national security. Many can protect themselves by temporarily shutting down sensitive systems when dangerous radiation is expected. That protection, however, depends upon recognizing the true severity of an incoming event. If a flare appears less energetic than it actually is, a spacecraft may remain exposed when it should have entered a safer operating state. The same challenge extends to aviation. During significant geomagnetic storms, airlines sometimes reroute flights passing near the poles, where Earth's magnetic protection is weaker and radiation exposure increases. Those operational thresholds are derived from the same scientific understanding of flare energy. A revised energy scale may eventually influence when such diversions become appropriate. Human exploration beyond Earth raises an even greater concern. Astronauts aboard the International Space Station still benefit from substantial protection provided by Earth's magnetosphere. Future crews traveling under the Artemis program toward the Moon or working on its surface will spend much more time outside that magnetic shield. Their allowable radiation exposure and emergency planning depend upon forecasts rooted in the same physical assumptions now undergoing revision. None of this suggests negligence or careless engineering. The safety margins built into modern space weather responses were developed using the best evidence available at the time. The challenge is that the underlying measurement itself now appears incomplete. Alexander Russell and his colleagues noted that incorporating the newly calculated ion temperatures could improve future forecasting accuracy. Yet, transforming a scientific result into trusted operational practice requires extensive validation, repeated testing, and international coordination. Until that work is complete, many of the forecasts guiding decisions around Earth continue to rely upon numbers that scientists now recognize as only part of the full picture. Step back from solar flares for a moment, and another puzzle comes into view. It has challenged generations of physicists, resisted decades of observation, and remains connected to the same magnetic processes we have already explored. Before we can fully understand the sun's most violent eruptions, we must confront the strange behavior of the atmosphere surrounding our nearest star. The expectation seems almost too obvious to question. Move away from a campfire, and the air becomes cooler. Leave any ordinary heat source behind, and temperature falls with distance. This follows the basic principles of thermodynamics, the branch of physics describing how heat moves through matter and energy. The rule applies across everyday experience and throughout much of the universe. Yet the sun refuses to cooperate. Its visible surface, known as the photosphere, reaches approximately 9,900 degrees Fahrenheit. Rising only about 1,200 miles above that glowing layer brings us into the corona, the sun's outer atmosphere. Instead of becoming colder, temperatures surge beyond 1,800,000 degrees Fahrenheit, while some regions approach 5,400,000 degrees Fahrenheit. The farther we travel from the apparent source of heat, the hotter the surrounding gas becomes. That contradiction is known as the coronal heating problem. Scientists have investigated it for more than 70 years, and despite remarkable advances in solar physics, no single explanation has earned universal acceptance. The mystery is not whether the corona is extraordinarily hot. Every observation confirms that it is. The unanswered question is how such temperatures are maintained. One leading idea involves Alfvén waves, named after physicist Hannes Alfvén. These are magnetic waves traveling through electrically charged plasma carrying energy upward from the sun's lower layers. If enough of that energy is deposited into the corona, it could help explain the extraordinary temperatures measured there. Another proposal focuses on nanoflares. A nanoflare is an extremely small burst of magnetic reconnection, the same process that powers much larger solar flares. Each individual event would release only a tiny amount of energy and remain too small for present instruments to observe directly. Collectively, however, countless nanoflares occurring across the corona could produce an enormous and continuous source of heating. The Parker Solar Probe provided an important breakthrough after entering the corona during April of 2021. Flying directly through this remarkable environment, the spacecraft detected Alfvén waves in place rather than observing them from afar. Their existence was no longer theoretical, and the measurements confirmed they carry substantial energy. Even so, researchers continue debating whether those waves alone can account for the entire temperature inversion. The mystery reaches far beyond academic curiosity. The corona is the birthplace of the solar wind and of coronal mass ejections that spread through the solar system. Whatever mechanism heats this outer atmosphere also shapes the sun's most hazardous activity. That connection makes the findings published during September of 2025 especially intriguing. Magnetic reconnection, the process shown to heat ions far more efficiently than expected, also stands among the principal candidates for powering nanoflares. The questions may not be separate after all. A corona whose heat remains only partly explained belongs to a sun whose full behavior still lies beyond complete prediction. You are never outside the sun's reach. Even at Earth's distance, every moment unfolds within a continuous outward flow of particles that began high above the solar surface and spread across the entire solar system. Our star does not simply radiate light. It also releases matter, expanding in every direction without pause. This flow is known as the solar wind. It consists primarily of electrons, protons, and alpha particles, which are atomic nuclei made from two protons and two neutrons. Escaping from the corona, these charged particles stream outward at speeds ranging from roughly 250 miles per second to about 500 miles per second. The flow generally moves more slowly above the sun's equatorial regions and faster near its poles, following the structure of the magnetic field. Despite its familiar name, the solar wind is not a breeze in the ordinary sense. It is a genuine stream of matter exerting measurable pressure on everything in its path. Every planet, moon, asteroid, spacecraft, and comet exists within that persistent current, immersed in material that originated inside the sun itself. Over immense distances, this outward pressure creates a vast bubble surrounding our planetary system. Astronomers call it the heliosphere, meaning the region dominated by the sun's influence. It stretches for roughly 100 astronomical units in every direction, with one astronomical unit representing the average distance between Earth and the Sunday. Beyond that enormous bubble, the material between the stars begins to compete with the fading pressure of the solar wind. Humanity has reached that frontier only once. During 2012, the Voyager 1 spacecraft crossed the heliopause, the boundary where the outward pressure of the solar wind balances the pressure of interstellar space. At approximately 121 astronomical units from the Sun, it became the first human-made object to enter the region between the stars, while continuing to transmit scientific observations. Closer to home, the solar wind reshapes Earth's magnetic shield every day. The magnetosphere is not truly spherical. Constant pressure compresses the side facing the sun while stretching the opposite side into a remarkably long magnetic tail, extending far beyond the moon's orbit. What you might imagine as a balanced protective shell is instead a structure continually molded by an invisible cosmic current. The northern and southern lights provide another visible reminder of this interaction. The aurora borealis and aurora australis appear when solar wind particles follow Earth's magnetic field lines toward the polar atmosphere, where collisions with atmospheric gases produce glowing curtains of light. Their beauty reflects the changing activity of the sun rather than a decorative feature of Earth's skies. Elsewhere, the consequences become even more dramatic. Mars lost its global magnetic field roughly 4 billion years ago. Without that planetary shield, the solar wind gradually stripped away much of its atmosphere until only about 1% of Earth's atmospheric density remained. Comet tails also reveal the same influence, always pointing away from the sun regardless of the comet's direction of travel. As researchers reconsider the greater energy released during solar flares, they must also examine whether the solar wind, driven by those eruptions, carries more energy than long accepted, reshaping models throughout the solar system. If you watched the sun every day for a lifetime, you would notice that its activity never remains fixed. Months of relative calm gradually give way to years filled with dark sunspots, powerful eruptions, and frequent magnetic disturbances before the pattern slowly eases again. The rhythm is neither perfectly regular nor entirely predictable, yet it has shaped solar science for nearly 2 centuries. This repeating pattern is known as the solar cycle. During solar minimum, very few sunspots appear, and major flares become less common. Activity then climbs toward solar maximum when sunspot numbers reach their peak, and the likelihood of powerful flares and coronal mass ejections rises dramatically. Although often described as an 11-year cycle, that figure represents only an average. Individual cycles have lasted as few as 9 years and as many as 14. The pattern first emerged through remarkable persistence. German amateur astronomer Heinrich Schwab spent 17 consecutive years recording sunspots almost every clear day. In 1843, he announced that the numbers rose and fell in a repeating cycle. His careful observations transformed what had seemed like random changes into one of the defining rhythms of our nearest star. Each solar maximum also marks a profound magnetic transformation. The sun's magnetic poles reverse, with north becoming south and south becoming north before the next cycle begins. This reversal is part of the magnetic engine driving the activity we observe, making every cycle both an ending and a beginning. The current cycle, known as Solar Cycle 25, has provided a reminder that the sun does not always follow expectations. During 2019, a panel assembled by the National Aeronautics and Space Administration predicted a relatively weak, below average cycle. Instead, activity exceeded those forecasts. During May of 2024, Earth experienced the strongest geomagnetic storm in 2 decades, reaching the highest category used for operational warnings. Auroras extended far beyond their usual latitudes, appearing across Florida, Texas, the Bahamas, and parts of northern India. The displays attracted widespread attention, yet another consequence received far less notice. Precision farming equipment across the American Midwest, which depends heavily upon satellite navigation during the spring planting season, experienced disruptions as geomagnetic disturbances reduced positioning accuracy. For many agricultural communities, the sun briefly became an unexpected factor in everyday work. History also preserves periods when the opposite occurred. Between approximately 1645 and 1715, the Maunder minimum brought remarkably few sunspots for about 70 years. Those decades overlapped with some of the coldest conditions of the Little Ice Age, accompanied in many regions by crop failures, famine, and social hardship across Europe. A shorter interval. The Dalton minimum between roughly 1790 and 1830 also coincided with cooler global conditions, during a time when volcanic eruptions further amplified climatic effects. These episodes do not mean the sun alone controls Earth's climate, yet they demonstrate that its changing behavior carries consequences reaching far beyond space itself. Combined with recent discoveries showing greater flare energies and forecasts that underestimated solar cycle 25, they remind us that predicting the sun remains one of the most demanding challenges in modern astronomy. There are moments in exploration when observing from a distance is no longer enough. Telescopes can reveal astonishing detail, and mathematical models can describe hidden processes, yet some questions demand a journey into the environment itself. That ambition inspired one of the boldest spacecraft ever constructed, designed to venture where no human-made object had traveled before. The Parker Solar Probe launched on August 12, 2018, with a mission unlike any previous attempt. Rather than orbiting at a comfortable distance, it would repeatedly dive toward the sun until it entered the corona itself, gathering measurements from within the very atmosphere that has challenged physicists for generations. Its speed is almost difficult to imagine. At its closest approach, the spacecraft reaches approximately 430,000 miles per hour, making it the fastest human-made object ever built. At that velocity, a journey from New York to London would require less than 4 minutes. Achieving such speed depends upon repeated close passes by Venus, whose gravity gradually reshapes the probe's orbit and allows it to fall ever deeper toward the Sunday. Approaching so closely creates an extraordinary engineering challenge. The side facing the sun must withstand temperatures exceeding roughly 2,500 degrees Fahrenheit. Only a few inches behind that exposed surface, however, delicate scientific instruments must remain near ordinary room temperature to function correctly. The difference is maintained by an advanced heat shield measuring about 4½ inches thick. Its structure combines carbon composite foam between carbon fiber panels, creating a remarkably effective barrier. The shadow cast behind that shield, roughly the size of a small car, protects the spacecraft throughout each close encounter. During April of 2021, the mission reached another historic milestone. Parker's solar probe crossed the Alphane critical surface, the boundary where the sun's magnetic field and gravity dominate the surrounding plasma before the solar wind fully escapes into interplanetary space. Crossing that boundary meant humanity had, for the first time, entered the outer atmosphere of a star. The discoveries quickly followed. Instruments detected Alphane waves directly, instead of inferring their presence from distant observations. The spacecraft also revealed that the solar wind is far from smooth. It contains abrupt reversals in magnetic field direction known as switchbacks, dramatic bends, whose exact origin remains under active investigation. Parker even passed through towering coronal streamers, the bright structures visible during total solar eclipses, collecting direct measurements of plasma that had previously been studied only from afar. Each close approach carries another unusual feature. Communication with Earth becomes impossible while the spacecraft performs its carefully programmed observations. Engineers at the Johns Hopkins Applied Physics Laboratory can do little except wait until Parker emerges and restores contact, hoping every system has functioned as planned. Those observations now form the most valuable collection of direct measurements available for understanding the corona and the magnetic processes shaping it. They also provide the essential real-world evidence needed to evaluate new theoretical results, including the revised ion temperatures proposed during 2025. At its final planned closest approach, Parker's solar probe will pass within only about 3,800,000 miles of the Sun's visible surface, far inside the orbit of Mercury, which never comes closer than roughly 29 million miles. Across the face of the Sun, dark regions appear and disappear with remarkable regularity. They seem almost modest against the overwhelming brilliance surrounding them. Yet those patches reveal where magnetic fields have become intensely concentrated. Counting them has long provided one of the simplest ways to estimate the level of magnetic activity unfolding inside our nearest star. Their arrangement also raises a question that has become increasingly difficult to dismiss. How powerful can the Sun truly become? During 2019, researchers published a study in the Astrophysical Journal using observations gathered by the Kepler Space Telescope. Rather than focusing only on our own star, they examined many stars resembling the Sunday. These were G-type stars, meaning they shared broadly similar surface temperatures, sizes, and internal structure with the star that anchors our solar system. By watching thousands of stars over many years, astronomers could observe rare eruptions that would almost never occur during a single human career. The results were striking. Sun-like stars proved capable of producing superflares, eruptions releasing between 100 and 10,000 times more energy than the largest flares recorded during the modern age of solar observation. Based upon the frequency of those events across the sample, the researchers estimated that a star resembling the Sun could experience such an eruption roughly once every 2,000 to 3,000 years. That interval overlaps remarkably well with the mysterious Mayake events recorded in the years 774 and 993. Those ancient spikes in radioactive carbon preserved within tree rings remain the strongest known evidence that Earth experienced extraordinary bursts of high-energy particles. Some scientists have suggested those events may represent ancient solar superflares, although the exact cause continues to be investigated. There is, however, an important reason for caution. Many of the stars observed producing superflares rotate more rapidly than the Sunday. Faster rotation generally strengthens magnetic activity, and stronger magnetic activity tends to support larger flares. Our Sun rotates comparatively slowly, making extreme eruptions less likely than around many of its stellar relatives. Less likely does not mean physically impossible. The known laws governing stellar magnetism do not forbid a superflare on the Sunday. They indicate only that such an event would probably occur less often. If the event recorded during 774 truly was a solar superflare, some estimates suggest it may have released between 10 and 100 times more energy than the Carrington Event. Humanity endured it because civilization possessed no electrical infrastructure capable of failing. The consequences today would extend far beyond regional blackouts. Satellite electronics throughout Earth orbit could suffer widespread damage. Radiation levels in low Earth orbit might become hazardous for weeks, while changes to the ozone layer could allow increased ultraviolet radiation to reach Earth's surface for months. The last possible event of that scale occurred when Charlemagne ruled as Holy Roman Emperor, and the compass represented one of humanity's most advanced electrical technologies. The revised ion temperature findings, published during 2025, do not increase the estimated frequency of superflares, yet they do establish that the lower boundary of solar flare energy is greater than researchers believed only months before. Electricity arrives so reliably that it is easy to imagine the grid as something permanent. Across continents, enormous transmission networks carry power every second of every day, supported by equipment expected to operate for decades. Yet one particular weakness has been understood for years, and it begins beneath our feet rather than in the wires stretching across the landscape. When a powerful coronal mass ejection disturbs Earth's magnetic field, it creates geomagnetically induced currents. These are slowly varying electrical currents generated within the ground itself as the planet's magnetic environment changes. High voltage transformers connect directly to Earth through grounding systems, allowing those unwanted currents to enter equipment never designed to handle them. The danger comes from the difference between the electricity transformers expect and the electricity they receive during a severe geomagnetic storm. Their magnetic cores are engineered for alternating current, which constantly reverses direction. Geomagnetically induced currents behave much more like direct current, flowing steadily enough to force transformer cores into magnetic saturation, a condition where they can no longer operate efficiently. Excess heat rapidly builds inside the equipment, damaging insulation and internal components long before the exterior reveals the full extent of the failure. Replacing those transformers presents another challenge entirely. Large high voltage transformers are not standard industrial products waiting inside warehouses. Each unit is custom engineered for a particular location within the electrical network, matching precise operating requirements developed over many years. Some weigh nearly 880,000 pounds, making transportation an engineering project of its own. Only a limited number of specialized manufacturing facilities worldwide produce equipment of this scale. Under ordinary circumstances, replacing a damaged transformer may require 1 to 3 years from design through installation. During a widespread geomagnetic disaster affecting several countries at once, that timeline would almost certainly grow longer because every damaged region would compete for the same manufacturing capacity. The limitation would not be rebuilding transmission lines, it would be constructing the transformers themselves. Within the United States, approximately 2,000 large high voltage transformers support the national grid. Many entered service long before geomagnetically induced currents became a major planning concern. Engineers have developed methods to reduce this vulnerability, including protective devices and operational procedures, yet upgrading every critical location demands substantial investment and has progressed gradually. The scale of the risk has been examined repeatedly. During 2008, the National Academy of Sciences estimated that an exceptionally severe geomagnetic storm could interrupt electrical service for roughly 130 million people across the United States. Full recovery might require 4 to 10 years, driven primarily by the pace of transformer replacement rather than reconstruction of the surrounding grid. Emergency planning agencies have acknowledged the same concern. The Federal Emergency Management Agency, the Department of Homeland Security, and comparable organizations throughout the United Kingdom, Canada, and the European Union have all published assessments recognizing severe space weather as a significant infrastructure hazard. Some electrical grid operators now maintain procedures for disconnecting selected long-distance transmission lines before an extreme storm arrives, reducing the enormous antenna effect that encourages geomagnetically induced currents. Those protective actions, however, depend upon forecasts that are both timely and accurate. As those forecasting models undergo revision, following recent discoveries about solar flare energy, the importance of understanding the sun becomes inseparable from protecting the electrical systems supporting modern civilization. Long before messages reach your phone or computer, they begin a journey through strands of glass lying across the deepest parts of Earth's oceans. Satellites carry only a small fraction of global internet traffic. The overwhelming majority moves through undersea fiber optic cables linking continents with pulses of light, creating an unseen foundation beneath modern communication. During 2021, researcher Sangeetha Abdu-Jyothi of the University of California, Irvine, published a paper titled Solar Superstorms: Planning for an Internet Apocalypse. Rather than examining electrical grids or spacecraft, the study explored a vulnerability that had received remarkably little attention despite supporting nearly every aspect of the connected world. Today, roughly 808,000 miles of undersea fiber optic cable cross the world's oceans. Together, they form the physical backbone of international internet traffic, carrying financial transactions, cloud computing, scientific data, business communications, and countless everyday conversations. Most people never consider these cables because they remain hidden beneath the sea, functioning continuously without attracting notice. The glass fibers themselves are surprisingly resilient. Light traveling through the cable is largely unaffected by geomagnetic disturbances. The greater concern lies with the electronic repeaters positioned along each route at intervals of roughly 31 to 93 miles. These devices receive fading optical signals, strengthen them, and transmit them onward. They are powered by direct current flowing along the cable, making them susceptible to geomagnetically induced currents during an extreme solar storm. The greatest danger exists at higher latitudes. Cables crossing the North Atlantic, the Arctic, and the North Pacific pass through regions where disturbances in Earth's magnetic field become especially intense. During a storm comparable to the Carrington Event, Jyothi's analysis suggested that numerous repeaters could fail across those routes, interrupting major links between continents, even if local communication systems remained operational. That distinction is important. Your neighborhood internet connection might continue functioning. Regional broadband networks could remain intact, and wireless networks within individual cities might still exchange information locally. The disruption would emerge where continents connect. International websites, overseas financial services, cloud infrastructure distributed across oceans, and global data exchanges could become unavailable for weeks or even months while damaged systems were repaired. No modern economy has experienced an interruption of intercontinental digital communication on that scale. Manufacturing depends upon suppliers located across multiple continents. Financial markets exchange enormous volumes of information every second. Airlines, shipping companies, research institutions, and emergency services increasingly rely upon global networks operating without interruption. The full economic consequences of losing those links remain difficult to calculate because there is no historical event of comparable scope. Before 2021, discussions of severe space weather focused overwhelmingly on satellites, global positioning systems, and electrical grids. The vast undersea cable network rarely appeared in those assessments, despite serving as one of civilization's most important technological foundations. As of 2025, no widely adopted engineering standard exists for protecting undersea cable repeaters from extreme geomagnetic storms. The pattern has become increasingly familiar. As human technology extends into new domains, the sun discovers another pathway through which its influence can reach the systems we depend upon every day. For almost every moment of human history, survival beneath the sky has depended upon protections we rarely notice. Above us, Earth's magnetic field deflects enormous numbers of charged particles. Surrounding us, the atmosphere absorbs much of the radiation that penetrates farther inward. Together, they provide shielding roughly comparable to more than 30 feet of water, creating an environment where life has flourished for billions of years. The moment you leave those natural defenses, the situation changes. Space is filled with energetic particles arriving from the sun and from distant explosions across the galaxy. Without Earth's protective envelope, the human body must confront an environment it never evolved to endure. Even astronauts aboard the International Space Station remain only partially removed from Earth's protection. Orbiting about 250 miles above the surface, the station still travels within much of the magnetosphere. That magnetic shield significantly reduces radiation exposure, yet astronauts typically receive doses comparable to roughly 150 to 200 chest X-rays during a year of normal solar activity. Careful mission planning keeps those exposures within accepted limits, but the background hazard never disappears. Conditions become considerably harsher on the moon. There is no global magnetic field to divert charged particles and virtually no atmosphere to absorb them. Astronauts working on the lunar surface face direct exposure to solar energetic particles, which are high-speed particles accelerated during major solar eruptions, as well as galactic cosmic rays arriving from far beyond our solar system. History contains a remarkable reminder of how much depended upon timing. During April of 1972, Apollo 16 explored the moon. Apollo 17 followed in December of the same year. Between those missions, during August, the Sun unleashed one of the largest solar particle events of the 20th century. Had astronauts been walking across the lunar surface during the peak of that eruption, spacesuits alone would probably have provided insufficient protection against potentially life-threatening radiation. Modern exploration plans reflect that lesson. The National Aeronautics and Space Administration has incorporated space weather response procedures into the Artemis program. Surface activities are designed around continuous monitoring of solar conditions, allowing astronauts to move rapidly into shielded habitats or structures protected beneath layers of lunar soil if dangerous particle storms are detected. Mars presents an even greater challenge. A journey using present-day propulsion requires approximately 7 to 9 months in each direction. Throughout that voyage, there is no planetary magnetic field, no atmosphere, and no practical refuge beyond the spacecraft itself. According to estimates from the National Aeronautics and Space Administration, a complete round trip approaches an astronaut's career radiation exposure limits, even if no major solar storm occurs. A powerful solar energetic particle event during transit could increase those risks dramatically. Researchers continue investigating antioxidants, compounds that support deoxyribonucleic acid repair, and other radioprotective medicines. Yet, no approved operational treatment currently provides the level of protection required for deep space travel. The near miss of 1972 is remembered today less for what happened than for what almost did. Human exploration succeeded because the astronauts had already departed while the sun erupted after they were safely home. Long before the first package reaches your doorstep or a passenger aircraft begins its descent, an invisible clock has already coordinated countless events across the planet. Most people associate the global positioning system with navigation, yet its greatest importance lies in something even less visible. It provides extraordinarily precise timing, allowing modern infrastructure to agree on exactly when every action occurs. Originally developed as a military navigation system, The global positioning system gradually became a foundation beneath the global economy. Banks, communications networks, transportation systems, and industrial operations now depend upon signals transmitted from satellites orbiting high above Earth. Many of those systems never appear on a map, yet they rely upon the same constellation that guides drivers through unfamiliar streets. A major solar flare threatens that dependence almost immediately. Intense bursts of electromagnetic radiation reach Earth in roughly 8 minutes, traveling at the speed of light. As that radiation disturbs the ionosphere, the electrically charged region high above the atmosphere through which satellite signals must travel, global positioning system accuracy begins to degrade. The effect arrives long before any coronal mass ejection reaches the planet. Financial markets illustrate how deeply that timing has become embedded in daily operations. Trading systems across multiple exchanges use global positioning system time signals to sequence transactions with extraordinary precision. Those timestamps help establish the exact order of trades, reducing errors and limiting opportunities for unfair advantages created by uncertain timing. A disruption affects more than navigation. It challenges the shared clock supporting electronic commerce itself. Agriculture has also become unexpectedly dependent upon those satellites. Modern precision farming guides, tractors, planting equipment, irrigation systems, and harvesting machinery with remarkable accuracy. During the severe geomagnetic storm of May 2024, disruptions to global positioning system performance affected agricultural equipment across portions of the American Midwest during an important planting period, even though the event received relatively little attention beyond farming communities. Commercial aviation depends upon the same precision. Thousands of airports rely upon satellite-based approaches that allow aircraft to land safely when visibility is limited. If space weather reduces positioning accuracy beyond acceptable limits, flight crews must return to older instrument procedures or divert to alternate airports until conditions improve. The dependence extends into everyday emergency response. Ambulances, fire departments, and many police agencies dispatch vehicles using continuously updated satellite positioning. Lost accuracy translates directly into longer travel times when every minute carries importance. Cellular networks share a similar vulnerability because neighboring base stations use global positioning system timing to coordinate the transfer of phone calls, text messages, and data connections as devices move between coverage areas. Global shipping follows the same pattern. Container vessels, cargo aircraft, freight rail systems, and long-distance trucking networks all assume uninterrupted access to satellite navigation and timing. Autonomous vehicles entering commercial service likewise incorporate global positioning system data as one of their fundamental sources of information. None were designed with prolonged worldwide satellite navigation outages as an ordinary operating condition. In that sense, disruption of the global positioning system is not a secondary consequence of severe space weather. It is among the very first signs that the sun has begun reshaping the technological world beneath our feet. Since the year 2010, one spacecraft has maintained an uninterrupted watch over the Sunday. While people sleep, work, celebrate, and travel beneath changing skies, the Solar Dynamics Observatory continues recording our star without pause. Every hour of every day adds another layer to one of the largest scientific archives ever assembled. Its instruments observe the entire visible face of the sun simultaneously in 10 different wavelengths of light. Each wavelength reveals material at a different temperature, allowing scientists to examine separate layers of the solar atmosphere at the same moment. Instead of seeing a single glowing surface, researchers can compare multiple thermal environments unfolding together, building something resembling a continuously updated three-dimensional map of solar activity. The pace of that observation is extraordinary. The spacecraft captures a full disk image approximately every 3/4 of a second, while transmitting roughly 1.5 terabytes of information back to Earth every day. Over more than 15 years, those observations have accumulated into an immense historical record, preserving countless eruptions, magnetic rearrangements, and subtle changes that would otherwise have vanished forever. That archive has transformed the study of solar flares. Scientists can now follow complicated magnetic structures as they twist, stretch, and interact before powerful eruptions occur. Regions where magnetic fields become unusually tangled often display a greater likelihood of producing significant flares. Watching those patterns evolve in near real time has improved the ability to recognize areas deserving closer attention. More recently, machine learning, a form of computer analysis that discovers statistical patterns within enormous collections of data, has been trained using the observatory's extensive archive. In several studies, these systems have outperformed traditional human forecasting methods when estimating whether particular active regions would produce major flares within the following 24 hours. Even so, improved prediction is very different from complete prediction. The obstacle lies within the nature of the sun itself. Its magnetic behavior follows the laws of physics, yet those laws interact through an immensely complicated system that responds to tiny differences in starting conditions. A slight variation can eventually produce dramatically different outcomes. You might recognize the same challenge from weather forecasting. Meteorologists often predict broad weather patterns several days ahead with impressive accuracy. Yet the precise behavior of an individual tornado can remain uncertain until shortly before it forms. Solar forecasting may possess similar limits that no amount of computing power can entirely overcome. The observatory has also revealed that the visible surface of the sun never remains still. It is covered by convection cells called granules, immense bubbles of hot plasma rising and falling over periods lasting roughly 8 to 20 minutes. Each granule spans an area comparable to the size of Texas. Beneath them lie even larger supergranules, and researchers continue investigating whether giant convective cells occupy much of the entire convective zone. Yet, some of the oldest mysteries remain unresolved. Despite 15 years of uninterrupted observations and decades of investigation into the unexpectedly hot corona, the complete explanation still eludes science. Even more revealing, mathematical work published during September of 2025 overturned a 50-year assumption embedded within interpretations of the observatory's own measurements. The lesson reaches beyond the sun itself. Gathering extraordinary amounts of information does not automatically correct the ideas used to understand it. Imagine the moment a major solar eruption begins. Across Earth, scientists, engineers, airline dispatchers, satellite controllers, and electrical grid operators all depend upon the same stream of observations. The remarkable truth is that the global warning system, protecting modern civilization, rests upon a surprisingly limited collection of spacecraft and observatories, each contributing measurements that must be interpreted within models still being refined. The National Oceanic and Atmospheric Administration operates the Space Weather Prediction Center in Boulder, Colorado, throughout every hour of every day. From there, forecasters issue alerts used by satellite operators, commercial airlines, electrical utilities, government agencies, and military organizations around the world. Those forecasts represent decades of scientific progress. Yet, during late 2025, the operational models had not fully incorporated the revised understanding of ion temperatures emerging from recent mathematical analysis. Far from Earth, another spacecraft performs an especially important task. The Deep Space Climate Observatory remains stationed near the first Lagrange point, a location where the gravitational influence of Earth and the Sun allows a spacecraft to maintain a relatively stable position approximately 930,000 miles from our planet. From there, it measures the magnetic properties of approaching solar material before that material reaches Earth. Those observations determine one of the most important details in space weather forecasting. A coronal mass ejection does not become equally dangerous simply because it is large. Its magnetic orientation strongly influences how efficiently it couples with Earth's magnetic field. That final measurement provides the last opportunity to judge whether an incoming eruption is likely to produce a severe geomagnetic storm. The difficulty is timing. Coronal mass ejections commonly travel between roughly 1,100,000 and 4,500,000 miles per hour. By the time they reach the first Lagrange point, the remaining warning window generally ranges from only 15 minutes to about 1 hour. That interval may allow satellites to enter protective operating modes, but it offers limited time for many large-scale electrical grid responses requiring careful coordination across extensive transmission networks. A longer warning has motivated plans for another observing platform. Scientists have proposed placing a spacecraft near the fifth Lagrange point, located roughly 60 degrees behind Earth along its orbit around the Sunday. From that position, an approaching coronal mass ejection could be viewed from the side, allowing its structure and trajectory to be analyzed much earlier. The European Space Agency designed the Vigil mission specifically for that purpose, with launch planned for the later years of this decade, though it had not yet flown by the middle of 2025. Until such observations become available, forecasting remains largely reactive. Solar telescopes detect an eruption leaving the Sun, estimate its path, and await confirmation from the Deep Space Climate Observatory shortly before arrival. The revised ion temperature findings add another layer of uncertainty because even an accurate arrival forecast may still underestimate the eruption's true energy. International cooperation continues to improve through organizations including the United Nations Office for Outer Space Affairs, while leading industrial nations increasingly recognize severe space weather as a shared challenge. Yet coordination alone cannot replace capabilities that have not been built, leaving preparedness more advanced than in past decades, but still short of the risks science now understands. No laboratory could ever reproduce the lifetime of a star. Even the longest scientific careers observe only a brief moment in the history of the Sunday. To understand what our own star may eventually do, astronomers have looked outward, treating the Milky Way itself as a vast natural experiment unfolding across billions of years. Current estimates place the number of stars in our galaxy between 100 billion and 400 billion. Space telescopes have transformed that immense population into something scientists can study statistically rather than individually. Instead of waiting centuries for one unusual event, researchers now watch thousands of stars at the same time, collecting evidence from many stellar lives unfolding together. The Kepler Space Telescope and the Transiting Exoplanet Survey satellite have recorded stellar flares across thousands of nearby stars. Those observations reveal how frequently different kinds of stars produce eruptions of varying strength, allowing astronomers to compare the Sun against a much larger cosmic population instead of judging it only by recent human experience. The most common stars are red dwarfs, also known as M-type stars. They account for roughly 70% of all stars in the Milky Way. Many remain magnetically active for extraordinarily long periods, especially during their younger years. Their flares can be vastly more energetic relative to their size than those produced by the Sun, bathing nearby planets with radiation levels thousands of times greater than Earth typically experiences. Our closest stellar neighbor provides a striking example. Proxima Centauri, located about 4¼ light years away, is a red dwarf that regularly produces powerful flares, including eruptions reaching superflare energies. Its planet, Proxima Centauri b, orbits within the region where temperatures might otherwise allow liquid water. Yet persistent stellar activity has made many researchers question whether its surface could sustain life for extended periods. Stars resembling the Sun generally display much calmer behavior. Even so, observations from the Kepler Space Telescope have documented superflares on G-type stars sharing many of the Sun's essential characteristics. Statistical analysis published during 2019 indicated that younger G-type stars, rotating more rapidly, produce those events more frequently. The Sun's slower rotation reduces the expected occurrence rate, although the underlying physics offers no indication that such eruptions are impossible. This broader stellar survey changes an important perspective. Human instruments have monitored the Sun in detail for only about 150 years, a remarkably brief interval compared with the lifetime of a star measured in billions of years. That record alone cannot define the complete range of solar behavior. The sample is simply too small. Tree rings preserve another line of evidence through the Miyake events, revealing extraordinary bursts of radiation during the years 774 and 993. Those ancient records agree surprisingly well with the statistical patterns emerging from observations of Sun-like stars. The mathematical work published during 2025 adds a third independent thread by showing that ordinary solar flares contain more energy than previous models assumed. Together, stellar surveys, ancient trees, and modern analysis all point toward the same conclusion. We understand the Sun most clearly by recognizing that it is one member of a vast stellar family, surrounded by countless examples of what similar stars have already revealed. When we speak about the Sun's influence on Earth, it is tempting to search for a single answer. Does the Sun drive our climate, or does it play only a minor role? Scientific evidence points toward a more nuanced picture. The relationship is neither absolute nor insignificant, and researchers continue refining their understanding as new observations accumulate. One measurement often discussed is total solar irradiance, the overall amount of solar energy reaching Earth. Across a typical solar cycle, that output changes by only about 0.1%. Climate scientists generally conclude that such a modest variation by itself is too small to explain the large changes observed in Earth's modern climate. The Sun's brightness does fluctuate, yet those fluctuations alone cannot account for every long-term trend. Other forms of solar energy behave differently. Ultraviolet radiation, which carries more energetic light than the visible spectrum, varies by as much as roughly 8% during a solar cycle. That difference matters because ultraviolet radiation strongly influences the chemistry of the stratosphere, the atmospheric layer where much of Earth's ozone forms. Changes there can alter temperature patterns high above the surface, affecting circulation that gradually extends into the lower atmosphere where weather develops. One of the most closely examined historical examples occurred during the Maunder Minimum, a prolonged interval between approximately 1645 and 1715, when sunspots became exceptionally rare. During much of that same period, Europe experienced some of the coldest winters associated with the Little Ice Age. The River Thames froze often enough that public festivals known as frost fairs were held upon the ice, an image preserved in paintings and written accounts from the era. Whether those colder conditions resulted primarily from reduced solar activity remains an active scientific question. Several major volcanic eruptions also occurred during that period, injecting particles into the atmosphere that reflected incoming sunlight and promoted cooling. Untangling the relative influence of volcanic activity and changing solar behavior continues to challenge climate researchers. Another proposed pathway involves the sun's magnetic field rather than its brightness. Known as the Svensmark hypothesis, this idea suggests that stronger solar magnetism reduces the number of galactic cosmic rays reaching Earth's atmosphere. Those high-energy particles may influence cloud nucleation, the formation of microscopic particles upon which cloud droplets develop. Increased cloud cover could reflect additional sunlight and cool the surface. Experimental and observational studies have produced mixed results, leaving the hypothesis both influential and debated. Some conclusions, however, attract broad agreement. The sun is not perfectly constant, and the roughly 150 years covered by detailed instrumental observations represent only a brief interval within its multi-billion year history. That relatively short record may include levels of activity that are not fully representative of much longer patterns. The mathematical findings published during 2025 concern the energy released during solar flares rather than the sun's average brightness, so they do not directly revise climate science. Even so, they reinforce a broader lesson that extends beyond this specific discovery. The sun influences Earth through several interconnected processes operating across different timescales. Some have been measured with considerable confidence, while others remain subjects of active investigation, reminding us that our nearest star still contains important chapters that science has yet to read. Every sunrise belongs to a star that is neither young nor old. The sun is approximately 4,600,000,000 years into its life, resting near the middle of its long main sequence stage, the prolonged period during which hydrogen in its core is steadily transformed into helium. Barring unexpected events, that process will continue for roughly another 5 billion years. Even across those immense spans, the sun does not remain unchanged. From the time Earth condensed from the swirling solar nebula until today, our star has gradually become brighter. Modern models indicate that it now radiates roughly 30% more energy than it did when the earliest oceans formed upon the young planet. The increase has been slow enough for life to adapt, while Earth's own geological processes helped maintain conditions favorable for liquid water. That balance cannot continue forever. About 1 billion years from now, increasing solar brightness is expected to overwhelm one of Earth's most important natural regulators, the carbon-silicate weathering cycle. This long-term geological process removes carbon dioxide from the atmosphere and helps stabilize planetary temperatures. As the sun continues brightening Atmospheric carbon dioxide gradually declines, plant life becomes increasingly difficult to sustain, and surface conditions slowly grow less hospitable. Eventually, persistent liquid water becomes increasingly difficult to maintain across much of the planet. Far later, another transformation begins. After roughly 5 billion additional years, the hydrogen fuel within the sun's core becomes exhausted. Fusion shifts into a surrounding shell, releasing energy that causes the outer layers to expand dramatically. The sun enters its red giant phase, swelling to nearly 200 times its present diameter and completely reshaping the inner solar system. Mercury disappears first, Venus follows. Earth's ultimate fate remains surprisingly uncertain. As the sun expands, it also loses mass through powerful stellar winds. With less mass, its gravitational pull weakens slightly, allowing Earth's orbit to drift outward. At the same time, interactions with the sun's enormously expanded outer atmosphere may produce enough drag to pull the planet inward. Current scientific models remain divided over whether Earth escapes as a scorched, airless world or is ultimately consumed within the expanding stellar envelope. The red giant stage is not the final chapter. Eventually, the sun sheds its outer layers into space, creating a planetary nebula, an expanding cloud of glowing gas stretching across light years. Despite its name, a planetary nebula has nothing to do with planets. Early astronomers simply thought these delicate clouds resembled distant planetary disks through small telescopes. At the center, the remaining core becomes a white dwarf approximately the size of Earth, containing much of the Sun's original mass compressed into an astonishingly dense object. A white dwarf does not explode, it simply cools. Over trillions of years, it gradually fades from white to yellow, then red, before eventually becoming a theoretical black dwarf, a remnant so cold that the universe itself is not yet old enough for one to exist. Meanwhile, the atoms released into the planetary nebula disperse through interstellar space, joining new molecular clouds that will someday form new stars, new worlds, and perhaps new living planets. Against that immense future, human civilization occupies only a fleeting instant, yet understanding the sun's complete life story gives deeper meaning to every ordinary day beneath its light. Long before the first observatory rose above a hillside, or the first equation described a star, people measured time by watching where the sun appeared along the horizon. Every civilization inherited the same daily rhythm. Long before astronomy became a science, survival depended upon recognizing patterns of light, season, and shadow with remarkable precision. One of the most enduring examples stands upon the plains of southern Britain. Stonehenge was constructed roughly 4,500 years ago, with its central axis carefully aligned to the midsummer sunrise and the midwinter sunset. That arrangement was no coincidence. It reflected generations of careful observation, preserved across centuries, until builders translated repeated celestial events into enduring stone. Ancient Egypt expressed the same understanding on an even grander scale. Temples were oriented along carefully chosen solar paths, requiring sustained astronomical observation across many years. At the great temple of Abu Simbel, sunlight reaches deep into the inner sanctuary on only 2 days each year, illuminating statues of the pharaoh and two deities. Those dates correspond to the traditional celebration of the ruler's birthday and coronation, demonstrating how architecture itself became a calendar written in sunlight. Far across the Mediterranean, another achievement revealed a different approach. The Antikythera mechanism, recovered from a shipwreck during the year 1901, but constructed around 100 years before the birth of Christ, used intricate bronze gears to calculate the movements of the sun and the moon. It functioned as an analog computer capable of predicting astronomical events with astonishing sophistication. Its differential gearing represented an engineering accomplishment that would not appear again in Europe until roughly the 14th century. Across the Andes, the Inca civilization shaped stone rather than bronze. At Machu Picchu, the Intihuatana stone served as an astronomical marker whose name is commonly translated as the hitching post of the Sunday. Around the equinoxes, when day and night are nearly equal in length, the midday sun passes almost directly overhead, leaving the carved monument with virtually no shadow. Observations such as these helped regulate agricultural calendars in a landscape where timing determined whether harvests succeeded. That dependence united nearly every farming society throughout history. Solstices and equinoxes were practical milestones marking the changing seasons. Planting too early risked frost. Planting too late shortened the growing season. Watching the sun meant protecting food supplies, communities, and future generations. Centuries later, during the Maunder Minimum, reduced solar activity coincided with some of Europe's harshest winters. Crop failures became more common, food shortages spread across regions, and prolonged economic hardship contributed to broader social instability that historians recognize as one factor among many shaping conditions that eventually led toward the French Revolution. Today, the relationship has changed in form rather than importance. Instead of depending solely upon sunlight to determine planting seasons, we rely upon electrical grids, satellites, communication networks, transportation systems, and data centers whose operation assumes the sun remains within the range of activity for which modern infrastructure was designed. Every generation has lived beneath the same star. What has changed is the depth of our dependence and our growing recognition that understanding the sun is no longer only an intellectual pursuit. It has become an essential responsibility for a civilization built upon electricity. Progress in science rarely follows a straight path. Each generation inherits explanations that seem complete, only to discover that a single new observation can reshape decades of understanding. Our study of the sun reflects that pattern with unusual clarity because every improvement reveals both how much we have learned and how much still remains beyond reach. During the early 19th century, the celebrated astronomer William Herschel, whose discoveries permanently changed our picture of the solar system, proposed that the sun might contain a cool interior beneath its brilliant outer layers. Given the observations available at the time, the idea appeared logical. Instruments capable of probing the sun's true structure did not yet exist, and many fundamental principles of stellar physics had not been developed. Herschel's reputation remained well-deserved, even though his conclusion proved entirely incorrect. Another chapter unfolded much later through one of the smallest known particles. Solar models predicted that nuclear reactions within the sun's core should produce about 3 times more neutrinos than detectors initially observed on Earth. For roughly 30 years, researchers debated whether the calculations describing the sun were flawed or whether the experiments themselves contained hidden errors. The eventual answer transformed particle physics. Neutrinos were changing identity while traveling through space, a process called neutrino oscillation, meaning early detectors captured only one variety. The sun had been behaving as predicted all along, while nature revealed a phenomenon no one had anticipated. Some mysteries remain unresolved even now. The coronal heating problem, the question of why the sun's outer atmosphere reaches temperatures far exceeding those of its visible surface, has challenged researchers for more than 70 years. Numerous explanations have been proposed, yet no single mechanism has gained universal acceptance. The question continues to motivate new observations, experiments, and mathematical models. The mathematical findings published during 2025 follow a remarkably familiar pattern. Measuring ion temperatures directly proved technically difficult, so scientists relied upon a more accessible quantity serving as a proxy, a substitute measurement expected to represent the value that could not easily be obtained. For roughly half a century, that assumption remained embedded within solar models. A new analytical approach eventually demonstrated that the substitute did not faithfully represent the underlying physical conditions, requiring decades of calculations to be reconsidered. That revision should not be mistaken for failure. It illustrates science functioning exactly as intended. Evidence is continually tested, assumptions are challenged, and improved methods replace older ones whenever observations demand it. Progress depends upon correcting mistakes rather than preserving them. The significance lies in what is being studied. This is not a distant object whose behavior affects only astronomical theory. The sun powers every climate system, shapes near Earth space, influences satellites, and defines the operating environment for infrastructure supporting modern civilization. Refining our understanding, therefore, carries practical consequences alongside scientific ones. Perhaps the most accurate description of solar physics today is also the most encouraging. We possess better telescopes, more capable spacecraft, stronger computers, and deeper mathematical tools than any generation before us. Even so, important revisions continue to emerge after decades of careful work. That combination of expanding knowledge, remaining uncertainty, and steady investigation is not evidence that science lacks reliability. It is evidence that understanding grows through continual refinement, especially when the universe proves more intricate than our first explanations. Stand outside, beneath daylight, for a moment, and you are participating in a relationship that has endured since before the first living cell appeared on Earth. The space between our planet and the sun is neither empty nor incidental. It is the stage upon which every chapter of our history has unfolded, defined by a distance that is both ordinary in astronomy and extraordinary for life. The average separation between Earth and the sun is about 93 million miles. Light crosses that span in roughly 8 minutes and 20 seconds. That interval is brief enough for sunlight to feel immediate, yet the distance itself places Earth within a narrow range where surface temperatures allow liquid water to persist. Had our planet formed appreciably nearer, the oceans would eventually have been lost. Farther away, they would have remained locked beneath permanent ice. There is nothing mystical about this arrangement. Earth formed where material happened to gather within the young solar nebula roughly 4,600,000,000 years ago, and those conditions proved suitable for life. That perspective transforms the sun itself. The same star capable of producing eruptions that challenge modern technology also occupies precisely the region that allowed technology to emerge. The balance is remarkable because both realities belong to the same object. Even the sunlight touching your face carries an astonishing history. Many of the photons arriving during an ordinary afternoon began their journey inside the sun's core between roughly 10,000 and 170,000 years ago. Before escaping into space, they wandered through dense layers of hot plasma, scattering countless times in a slow outward migration lasting far longer than modern humans have existed. Once free, those same photons crossed 93 million miles in little more than 8 minutes, before reaching one place, one person, and one moment. Nearly every source of energy that has sustained civilization traces back to that continuing stream of sunlight. Wood stores solar energy captured through photosynthesis. Coal, oil, and natural gas preserve ancient sunlight locked within long vanished ecosystems. Wind forms because uneven solar heating drives atmospheric circulation. Rivers flow because sunlight powers evaporation and rainfall. Even the food sustaining every living creature ultimately depends upon plants converting sunlight into chemical energy. Only geothermal heat from Earth's interior and nuclear fission originate elsewhere. Each breath tells the same story. The oxygen entering your lungs exists because photosynthesis has operated for approximately 3 billion years, gradually reshaping Earth's atmosphere through the persistent work of sunlight interacting with chlorophyll. Mars offers a revealing contrast. After losing its global magnetic field, the planet became increasingly vulnerable to the solar wind, the continuous flow of charged particles escaping the sunday. Much of its atmosphere disappeared, leaving behind a cold world with atmospheric pressure near 1% of Earth's at the surface. If life once flourished there, it faced a profoundly different future beneath the same star. The sun's influence reaches even farther than its light. Its gravity extends outward through the distant Oort cloud, a vast reservoir of icy bodies stretching roughly 2 light-years from the sun, farther than halfway to the nearest star. There is no precise boundary where the sun simply ends. From its flowing particles to its gravitational embrace, every planet, moon, comet, and asteroid exists within an immense domain shaped by the same star that has always made our existence possible. From the perspective of the galaxy, the sun occupies no privileged place. It drifts through the Orion Arm, a relatively open region located about 26,000 light-years from the center of the Milky Way. Around it stretches a stellar population estimated at between 100 billion and 400 billion stars, each following its own path through the same vast spiral structure. Our star completes one circuit around the galaxy in roughly 225 million to 250 million years, a span astronomers often call a galactic year. The last time the sun occupied approximately this position relative to the galactic center, the first dinosaurs were beginning their long history upon Earth. Entire chapters of evolution fit within only a small fraction of a single galactic orbit. The sun also carries the history of stars that lived long before it. Astronomers classify it as a population, one star, meaning it belongs to a comparatively recent generation formed from material enriched by earlier stellar lives. The iron concentrated within Earth's core, the calcium strengthening every bone, and much of the oxygen filling today's atmosphere were forged inside ancient stars through nuclear fusion before being scattered across space by stellar explosions. Long before Earth existed, those atoms traveled between dying stars and dark molecular clouds. Many researchers believe the birth of our own solar system may have begun with another violent event. About 4,600,000,000 years ago, the shockwave from a nearby supernova may have compressed part of a giant molecular cloud until gravity took over, beginning the collapse that eventually formed the Sun and the surrounding planets. In that sense, the destruction of one star may have provided the conditions required for another to begin. Looking beyond our galaxy expands the scale almost beyond imagination. Current estimates suggest the observable universe contains roughly 2 trillion galaxies. Each holds hundreds of billions and sometimes trillions of stars. The total stellar population almost certainly exceeds the number of grains of sand across every beach and desert on Earth by many orders of magnitude. Against that backdrop, the Sun appears thoroughly ordinary. It is a middle-aged G-type main sequence star with average mass, average brightness, and an unremarkable location inside an ordinary spiral galaxy. Yet your relationship to it changes everything. At only about 8 light minutes away, it is the only star close enough for spacecraft to approach directly, for instruments to observe continuously, and for discoveries to be tested against measurements returning to Earth within minutes. Nearly everything humanity understands about stellar interiors, nuclear fusion, magnetic cycles, coronal mass ejections, and stellar evolution has emerged primarily from studying this single nearby star. It serves as the key for interpreting countless others scattered across the universe. That is why the mathematical breakthrough announced during September of 2025 carried implications extending far beyond our own solar system. The revised understanding emerged from data gathered close to home rather than from distant observations. If ions inside the Sun are consistently hotter than decades of models assumed, then the same physical processes are likely shaping ordinary stars throughout the galaxy. A deeper understanding of one familiar star therefore becomes a deeper understanding of billions more. There is something remarkable about the particular moment in which you happen to exist. For approximately 4,600,000,000 years, the Sun has shone over Earth. During most of that immense history, no living creature could understand its light. No civilization depended upon electrical systems vulnerable to its storms, and no mind could ask why this ordinary star behaved as it did. When the Carrington Event erupted during the year 1859, it was not necessarily the greatest outburst the Sun had ever produced. It was simply the first to encounter a world beginning to weave electricity into daily life. The years that followed have steadily expanded that relationship. During roughly the last century and a half, dozens of powerful geomagnetic storms have swept past Earth. In 2012, a coronal mass ejection of extraordinary strength crossed Earth's orbit only after our planet had already moved beyond its path. During September of 2025, a new mathematical analysis revealed that ions within solar flares carried substantially more energy than researchers had assumed for decades. None of those discoveries signaled that the Sun had suddenly changed. Our understanding did. That pattern deserves careful attention. The measurement was technically demanding. A practical substitute became accepted. The substitute remained useful until a better method finally exposed its limitations. The correction arrived because someone looked again with different tools and different mathematics. That is neither failure nor surprise. It is the rhythm by which reliable knowledge slowly advances. Yet the scale of the revision is worth considering. The Sun is the most closely studied star in existence. Dedicated spacecraft observe it continuously, with some instruments recording new images every 3/4 of a second. Entire scientific careers have been devoted to understanding its magnetic fields, plasma, radiation, and internal structure. Even so, a foundational estimate describing flare energy remained incomplete for roughly half a century before a new approach revealed the difference. Perhaps that should reshape confidence rather than diminish it. Complex natural systems rarely surrender every secret at once. Each answer expands the landscape of meaningful questions. The Sun also connects to us in a deeper physical sense. Every atom of carbon, nitrogen, oxygen, and iron within your body originated inside earlier generations of stars. Those stars ended their lives. scattered their elements across interstellar space, and enriched the cloud that eventually formed the solar system. Over roughly 4 billion years, chemistry on Earth organized that ancient material into living organisms capable of tracing their own origins back through cosmic history. The people who aligned the stones of Abu Simbel with the changing path of sunlight were engaged in the same enduring pursuit as the researchers who developed the mathematical framework published during 2025. Their methods differed by thousands of years, yet both sought to understand the same star. Human civilization occupies only about 10,000 years of history. During that span, the Sun has completed only an almost immeasurably small fraction of a single orbit around the Milky Way. We have observed it with scientific instruments for roughly 150 years, and with spacecraft for only about 60. Knowing how much has already changed within those few decades, perhaps the most meaningful question is not how much we know today, but how much of today's certainty will become tomorrow's first approximation. History often remembers disasters by what happened afterward rather than by what almost happened. The Sun has offered several demonstrations of its power across the modern age, each revealing a little more about the relationship between our civilization and the star that sustains it. Whether those moments became global turning points depended less upon the Sun itself than upon circumstance. During the Carrington Event of 1859, powerful geomagnetic disturbances surged through telegraph networks, damaging equipment and igniting fires inside some telegraph offices. At the time, those systems represented the most advanced electrical technology humanity possessed. The event entered history as an extraordinary curiosity because the world had relatively little infrastructure capable of suffering broader consequences. More than a century later, the balance had changed. During May of 1989, another major geomagnetic storm caused the electrical grid serving Quebec to collapse in only 92 seconds. Roughly 6 million people lost power. Electricity returned within about 9 hours, and although important equipment experienced severe stress, the most critical transformers survived. The event demonstrated genuine vulnerability while remaining limited enough that modern society continued largely unchanged. Another warning arrived during July of 2012. A powerful coronal mass ejection crossed Earth's orbital path only after our planet had already moved beyond the impact point by approximately 9 days. Outside the community of solar researchers, relatively few people remember that near miss today. Its importance rests not in what occurred, but in what timing prevented. Then came the mathematical revision published during September of 2025. It concluded that ions within solar flares possess substantially more energy than decades of accepted models had estimated. That discovery remains, for now, a scientific result. It has not forced satellites into emergency operations, altered routine forecasting procedures, or produced immediate global disruption. Knowledge changed before events demanded it. Taken together, these moments reveal a consistent pattern. The Sun demonstrates its capabilities. Humanity escapes the most severe consequences because of timing, geometry, fortunate circumstances, or resilient engineering. Preparations improve afterward, yet often by smaller steps than the evidence itself might justify. The remaining question is practical rather than philosophical. Is gradual preparation sufficient for a natural hazard that provides no advance schedule, varies with changing solar activity, and is now understood to carry greater flare energy than previously believed? Researchers have recognized the vulnerability of large electrical transformers for decades. Concerns regarding undersea communication cables have likewise been explored through detailed studies. The recent revision to flare energetics adds another layer of understanding rather than introducing an entirely unfamiliar problem. The distance between scientific knowledge and practical readiness, therefore, cannot be explained simply by missing information. It also reflects competing priorities, limited resources, and the enduring challenge of preparing for events that appear distant until the day they arrive. The sun asks nothing of us. It continues, fusing hydrogen, generating magnetic fields, and releasing energy according to the same physical laws that have governed it for approximately 4,600,000,000 years. The real question belongs to us instead. If a civilization can discover that its nearest star is more energetic than it believed for half a century, can that same civilization organize itself to act upon that understanding before physics offers another reminder? Night does not mean the sun has stopped. While darkness settles over one side of Earth, our star continues pouring charged particles into space. The solar wind keeps flowing across the solar system. Earth's magnetic field continues responding to that invisible stream, bending, compressing, and redirecting it. Near the polar regions, particles released during earlier solar activity continue descending into the upper atmosphere, producing auroras beyond the glow of many cities, whether anyone happens to witness them or not. Within a few hours, the same sun will appear above the horizon once again. It has maintained that uninterrupted rhythm for approximately 4,600,000,000 years, and current models indicate it will continue doing so for roughly another 5 billion. The entire story of humanity has unfolded during a comparatively stable interval in the middle of the sun's life, an interval long enough for civilization to emerge while remaining brief against stellar time. During only about 150 years, people learned to generate electricity, connect continents through communication networks, launch thousands of satellites, and send robotic explorers beyond the known planets toward interstellar space. Every achievement depended upon a star that remained sufficiently predictable for those systems to survive and expand. The mathematical findings published during September of 2025 do not overturn that history. They refine it. Solar flares appear to contain more energetic ions than decades of models suggested, indicating that the margin separating routine conditions from severe disruption is somewhat narrower than previously believed. The sun itself has not become hotter or more active because of that discovery. It has always behaved according to the same underlying physics. The revision occurred within our understanding, exactly as scientific progress has repeatedly demonstrated throughout history. Far beyond the planets, the Voyager 1 spacecraft continues transmitting faint signals from interstellar space beyond the heliopause, the boundary where the outward flow of the solar wind yields to the material between the stars. Those transmissions, traveling at the speed of light, require more than 22 hours to reach Earth through the antennas of the Deep Space Network. Even there, at that extraordinary distance, the spacecraft has not yet reached the distant Oort cloud, and it remains within the Sun's immense gravitational domain. In a physical sense, everything belonging to the solar system exists inside the influence of the Sunday. Every planet, moon, comet, asteroid, spacecraft, and fragment of dust occupies a region shaped by its gravity, light, magnetic fields, or outward flowing particles. Those boundaries fade gradually rather than ending at a single dividing line. When Alexander Russell and his colleagues at St. Andrews published their analysis, it appeared in a scientific journal unfamiliar to most people and examined a temperature measurement few outside solar physics would ever consider. Yet, the mathematics revised a value supporting forecasts intended to protect modern infrastructure. Transformative discoveries often arrive in exactly that way. They emerge from careful examination of something already familiar, revealing unexpected depth within what seemed well understood. Tomorrow morning, the sun will rise over a civilization that depends upon it completely, understands it more deeply than ever before, and is still discovering what kind of star has illuminated every day of its existence.